Welcome to another edition of Math for No Reason. In this edition, we will be proving this beautiful identity, which is e to the power I pi is equal to minus. Let us start by trying to understand the expression e to the power I pi, and then we will show that e to the power I pi is equal to minus 1. Now, in complex analysis, for z a complex number, we define e to the power z as 1 plus z square by 2 factorial plus z cube by 3 factorial. So the exponential series for complex numbers is identical to the exponential series for real numbers, but with x replaced by the complex number z. Now, with this definition, we can prove another result which will be extremely useful for proving the identity e to the power I pi is equal to minus 1. Now, to get to that result, we must recall the two famous Taylor series expansions of sin x, which is x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and so on. And also that of cos x, which is 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial plus x to the power 8 by 8 factorial, and so on. Now, these two Taylor series expansions, along with the definition of the exponential function with complex argument, we will be able to derive a very famous result. So let us proceed. Let z be e to the power ix, where x is a real number. Then from the above definition of e to the power z, we get the following. Now, if we use the fact that I square is equal to minus 1 and separate out the real and complex parts, then what we get is 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial, so on. And the imaginary part is I into x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial. We note that using the two Taylor series expansions that we have written, cos of x is the real part and sin of x is the imaginary part. So we can write down e to the power ix as cos of x plus I sin. This is a very important identity, often referred to as Euler's identity. Now, if for x I put pi here, then this becomes cos pi plus I sin pi, and sin pi being 0 and cos pi is minus 1, so I get e to the power I pi is equal to minus 1, which is what we had started out to prove. Now, the expression e to the power ix is equal to cos x plus I sin x also tells us an important correspondence of these complex numbers with points on the unit circle. And if you think of this as the circle, then if you look at this angle x, then from elementary trigonometry you can see that the coordinates of these points is cos x, sin x. So we can think of every complex number of the form e to the power ix to be a point on the unit circle. Now, if I take x to to be equal to pi by 2, then we get e to the power I pi by 2 is equal to cos pi by 2 plus I sin pi by 2, which gives us I. Because cos pi by 2 is 0 and sin pi by 2 is 1. So e to the power I pi by 2 is equal to I. That means we can think of I to be a rotation in an anti-clockwise direction by an angle of pi by 2 radian or 90 degrees. So we can think of I to be an operator which takes any point on the unit circle and turns it through an angle of 90 degrees. And this interpretation is very helpful in trying to understand this identity e to the power I pi is equal to -1, because we see that if we start at 1 and take an anti-clockwise rotation by an angle pi, we get -1. So e to the power I pi is equal to -1 is consistent with the interpretation that we have. And also note that we first can move by 90 degrees and move from 1 to I here, and again we can apply I to this point to come to -1. So e to the power I pi by 2 into e to the power I pi by 2 gives us -1, which is again consistent with the fact that I square is equal to 1. So the interpretation of I as an anti-clockwise rotation operator which rotates through an angle of 90 degrees is a very powerful representation for understanding of complex number. Thank you.